game changer. I'm a risk taker.
Hello everyone and welcome to my video presentation for the RoboCup Asia-Pacific 2021 Aichi Japan RCAP CoSpace Autonomous Driving Challenge Under 19 League. I am 𝗘𝗲𝗍 from Bukit Panjang Government High School in Singapore. Let me tell you more about myself. I am 15 years old and I have taken part in several competitions in the past. Some include National Robotics Competition, NRC, in 2019 and 2021, and I achieved distinction in the RCAP Singapore Open earlier this year. Allow me to give you a summary of the preliminary round. Before I started to program the CoSpace bot, I had to do some planning, and there are two things to look out for when planning the route. The first is speed. The speed of the bot is crucial in achieving a better timing, as greater speed reduces the time taken to cover a certain distance. The second is length. Efficiency is key when achieving the fastest time. Time cannot be wasted on unnecessary turns and long routes. Thus, the length of the route must be as short as possible. The task for the preliminary round is to start in the area marked with the blue circle, then stop at all 5 checkpoints for 2 seconds and with blinking LED lights, and finally ending in the zone marked with the red circle. The image is in black and white to make the circles more distinguishable. After much planning, which I will talk about later, I came to use the route marked in light blue as it consisted of a lot of straights. The fastest route from point A to point B is a straight line, hence minimizing the turns is key, as well as not staying too far from the current checkpoint and the next checkpoint. It was also the shortest path, trying to get from the closest to the furthest checkpoint without any unnecessary turns. The following slides will break down my thought process when trying to choose the best route. The first to the second checkpoint. The straight line from the first and the second checkpoint is marked by the yellow arrow. There are two possible routes, the light blue one and the red one. I took the light blue one for a reason, despite it being further from the yellow line than the red one. This will be explained later. The second to the third checkpoint. The straight line from the second and the third checkpoint is marked by the yellow arrow again. There are two possible routes, the light blue one and the red one again. As you can see, the red one is longer and less straightforward. As you can see for both routes, red and light blue, the bot must be facing the right. This means that the red route from an earlier slide is less efficient, as the car would have to perform a 180 turn to face the right, which is a waste of time. The third to the fourth checkpoint. The straight line from the third checkpoint to the fourth checkpoint is again marked with an yellow arrow. There is only one option here, as the path is straightforward. It is clearly the only good route that satisfies the close to the yellow line and least number of turns requirement, having only one right turn and is relatively close to the yellow line. And lastly, the fourth to the fifth checkpoint. The straight line from the fourth and the fifth checkpoint is marked with a yellow arrow. The blue line is closer to the yellow arrow than the red one, meaning the blue route is more straightforward and is thus shorter. And when we put all of the blue routes together, get this route that I used and that I've shown before. Surprisingly, I managed to get an end in the first 10 tries, as in the Singapore Open preliminary round, it took me about 2 hours just to get a complete run. My initial timing after running that route was 46.105 seconds, which was pretty good for me. However, there were improvements to be made. Let's move on to the strategy and algorithm. I used the AI GUI present in the CoSpace Simulator instead of using the Python language for two reasons. Python makes the bot less reliable, and the line tracing is sloppier, the color sensors miss the reading. And also, I used the AI GUI in the RCAP 2021 Singapore Open earlier this year, and thus I am more familiar with the AI GUI than I am with the Python language for CoSpace. While the AI GUI had some restrictions, some of them being the topmost statement has more priority than the bottom statement, the AI GUI is less versatile in terms of making new variables and calculations, etc. etc. And the advanced action and advanced condition allows the AI GUI to have the versatility of a coding language, whilst also having the intuitive design of the AI GUI to code statements. The advanced action and advanced condition allowed me to work around the strict statement hierarchy by having the highest statements trigger only when a specific condition has been met, thus preventing the highest statements from triggering prematurely and overriding the core functions like line tracking, while also allowing the statements to activate while the line tracking is active when necessary. I will go more in depth about this later. One of the challenges I faced was the grey strip. As seen from previous slides, the route that I took was the fastest route I could run. However, using that route would mean I have to encounter 3 of these grey strips marked with the red ovals. The problem was that they were wide and there was no line to track. On top of that, the last one was bended. The solution was simple. I would do an inverted line track. Since the edges of the strips were white, I could make it such that when the edge light sensor senses the white edge, it would turn slightly. For example, if the right light sensor senses white, it would turn left, as that would mean that the right of the board would be sensing the edge and would have to turn left to go back on track. At the yellow strips, I would set a custom variable called inverse line track from 0 to 1. I had to improvise with 0 and 1 as there were no booleans. This would allow me to only activate the inverse line tracking algorithm when it needs it to be on. At the cyan strips, the variable inverse line track is then set back to 0 to stop the inverse line tracking algorithm from activating outside the grey strip. Now, let me talk about the statement priority. We all know that there are colored markers on the side of the line in some areas. Sometimes, they are needed to trigger a turn or to activate a certain action. However, these markers still have lines that allow the bot to line track. Therefore, if the statement that senses the color markers are beneath the line tracking algorithm, since the line tracking algorithm takes precedence, it would miss the colored markers. Hence, we can only put the colored marker statement above the line tracking algorithm. However, this might cause annoying problems. If the color sensor misreads a dark purple as a dark blue, it might trigger an unwanted turn or run an unwanted algorithm. Another problem arises when the color sensor is reading the edge of a black line and a white road, which makes the RGB reading AAA, where A is an integer between 0 and 255. Since it's sensing the in-between of a black line and the white road, the color sensor will be tricked into thinking that it sensed a grey color. All shades of pure grey have the same red, green and blue value, hence AAA. If a color sensing statement sets the range as R100 to 200, G 50 to 110, and B 90 to 150, the integer A is between 100 to 110, triggering the statement, causing an unwanted action. The solution is once again simple. To avoid misreading the values, ensure the RGB values are not all overlapping at once. For example, the statement will not and should not trigger if all the RGB values are the same, thus it will not trigger when it senses a certain value of grey. The second solution is to make the range as tight as possible. If the range is X and Y, where X is the lowest value and Y is the highest value, make it such that Y minus X is less than or equal to 15. Next, I will talk more about the PID line tracking. What exactly is PID? PID stands for proportional, integral, and derivative. Proportional means that the difference between the speed of the wheels, or should I say the amount of turning for the bot, is proportional to the error. The error in this case is defined as the distance of the center of the bot to the line. If there is a lot of error, it will turn more to correct for the error. This allows for a smooth line track. Integral. The error from the past is accounted for. If the cumulative error is not near 0, the bot will make a turn, thus not allowing a missed turn. Let me explain more about that. If the bot goes past a 90-degree turn because it is moving too fast, it will know that there is an error unaccounted for and will thus turn accordingly. The integral variable will reach 0 every time the bot is aligned, as when the bot is aligned, it ensures that all of the errors have been accounted for. Lastly, derivative. The bot will make a damping effect based on the rate of turn. If the bot turns right very fast to correct itself, there is a chance that it will overshot and the left light sensors will sense the line and turn left. This drastic turning will keep repeating until it's realigned, and this is known as oscillation. Oscillations waste time by making a straight path wavy, thus adding length to the run. Derivative helps by ensuring that if the bot turns too fast to the right, it will predict it, provide a counter turn to the left to hold the momentum before oscillation occurs. This also ensures a smoother line tracking. As you might know, if you want the best and most optimized line tracking, you would use all three aspects: proportional, integral, and derivative. Despite somewhat understanding the basics as well as the benefits of PID line tracking, I only used the proportional aspect of PID. The integral aspect could be added, but it would cause the simulation to be a bit slow. Oftentimes, the bot would take in too many variables and the frame rates would drop. This would lead to poor line reading, and the integral function would not only not work, but it would also harm line tracking. The derivative function could be used, but my line tracking was smooth and I did not want to overload my computer. Hence, I also did not use the derivative function. Now to talk about my final time and the recreated run. After many attempts and using all of the strategies mentioned in the previous slides, I achieved my best timing of 31.955 seconds. Despite this achievement here, I could not replicate the timing due to the recording software I was using, OBS, decreasing my frame rates. I will now show you the recreation of my run. Do note once more that the timing shown here might greatly differ from the actual run due to the lowered frame rates. Please enjoy. Now that I've shown you the run, let's move on to my reflection. Here are the areas for improvement. Although my run was optimized as much as possible, I felt that I could have made more improvements. I felt like I could have used the full extent of PID to make my bot smoother and more consistent. I felt like I could have saved more time if I had used a more consistent and reliable inverse line track algorithm, and I could have used the compass to move through some straight paths easier and more accurately. After the preliminary games, I learned a few important things. I learned how to better plan my route and learned the thought process on how to make the most efficient route. I learned how to optimize my run by making the line track smoother. I also learned how to potentially use all of PID to optimize my line tracking. Finally, I learned how to manage my time so as to not waste so much time trying non-viable strategies, as there are only 3 hours in the finals. In conclusion, I felt like I did well in terms of my run, but I could have done better and put in more effort into making the run as optimized as possible. Overall, I was satisfied with my timing, and I hope to keep it up and maybe even do better in the finals. That's all for my video presentation. Thank you for watching.